Probably anyone that you'd like. So we're just starting off again and we've had a question about which images would be the best to work on, and that has to be your choice on any pictures that you like or that are important to you or the applications that you're working with. So tonight we're going to look at reconstruction from projections. And I have a unique opportunity at this time to slip in a solution to problem 2.6b that I think everyone has had a chance to look at now, and maybe we'll discover the basic idea and the basic thing that was discovered by Ron Bracewell initially in 1955, and then when it was implemented in hardware, two people last year got the Nobel Prize. McCormick and Hounsfield both got the Nobel Prize for this same type discovery, and let's see if we can see the same thing. Or they implemented the discovery in hardware. It's now saved a lot of people's lives. Okay, problem 2.6 was one where we were given a line spread function, right? And we called it L of xy, and it was an integral over all space of a point spread function. Oops, we might have called it h of xy with respect to y, and so it will only come out L of x. Okay, the line spread function is a very interesting function. Notice that it can be called a projection function, but it's different from the type projection we did when we talked about an orthographic type projection. That if we have a two-dimensional function h of xy over here, and we integrate it with respect to y, up and down lines like this, we would generate just a function of x. And that's what that particular line spread function is. Now, we were given the case where the line spread function was something, and in fact, we were given that L of x was equal to the exponential of minus 0.7 times the absolute value of x. So it wouldn't look like this one, but as a function of x would look more like this. Now, the problem in this case was to determine the point spread function h of xy. And this is a very difficult problem. There have been probably at least a half dozen papers written about line spread functions and point spread functions in the literature. So it's a problem that is difficult enough that its solution has been written up in the Journal of Optical Society of America on different ways to compute these. And it turns out that there's even a special transform called the Abel transform that relates a point spread function and a line spread function. So that if we talked about the relationship between h of xy and L of xy, those are an Abel transform pair. But let's see if we can discover another way to look at this same problem where we want to determine h of xy. And we'll do it just for the case where we have a circularly symmetric function as we were given in this particular problem. Let me just first write down the two-dimensional Fourier transform expression. So if I wrote down the two-dimensional Fourier transform of the point spread function, it's an equation of this form. Where we integrate over all x and y values. Okay, so far I don't see anything too much, but let me play with this a little bit and say, okay, I have a double integral here. Up here I just have an integral from minus infinity of h of xy not multiplied by anything and integrated with respect to y. Could I manipulate this? What if I in fact set v equal to 0 and then rewrote this particular expression? Let's look at h of u and 0 for v. It would now be equal to an integral from minus infinity to infinity, another integral from minus infinity to infinity, h of xy, and now if I had v equal to 0, I could bring the integration with respect to y first inside, then multiply it by this complex sinusoid that now would just be e to the minus j 2 pi ux and integrate with respect to x. Now notice that this integral is exactly the function that we call the line spread function. So what does this tell me about how to solve this? Furthermore, notice that the rest of the integral, this integral from minus infinity to infinity, the complex exponential, and the other integration are simply a Fourier transform operation in one dimension. Right? So if I put L of x in here, then all this really is the one-dimensional Fourier transform of L of x. Because I have L of x e to the minus j 2 pi ux dx. So now, could I say this in any kind of words? So I've got the line spread function, its one-dimensional Fourier transform equal to the two-dimensional Fourier transform along the v equals 0 axis. Let me sketch that out and see just the the uv spatial frequency plane. V equals 0 would be right along this particular line, right? So h of u and 0 would be the values just along this axis in the two-dimensional plane. So now let me first solve problem 2.6b, and then let's see how it generalizes into a very useful technique. Okay, so this tells me a couple of things. First of all, if I take the one-dimensional Fourier transform of the line spread function, I get one line in the two-dimensional Fourier transform space. If this function is circularly symmetric, then all I have to do is rotate that function, or actually put r in for the u value, and I have h of uv over the entire space. And if I have h of uv over the entire space, I simply have to do the inverse transform to get h of xy over the entire space. So let's do that for our example of this line spread function of the I, where we're assuming it's circularly symmetric. Let me slip over to another board and do this again. So we have the line spread function of the I was exp to minus 0.7 times the absolute value of x for x from minus infinity to infinity. I want the Fourier transform of this, so I would have an integral from minus infinity to infinity of exp to minus 0.7 times the absolute value of x times the other kernel exp to the minus j 2 pi ux, and I would integrate that with respect to x. And this would all be equal to h of u and 0. Okay, so I can simplify this without any integration tables about the Abel transform, Hankel transform, or anything, and combine the arguments of the exponential term it would be minus 0.7 times the absolute value of x minus j 2 pi ux dx. And to get rid of the absolute value, let me break this up into two integrals, one from minus infinity to 0, and the other from 0 to infinity. And this term would be e to the, for values where x is negative, this is going to be minus x, so this would be plus 0.7x minus j 2 pi ux. And where x is positive, absolute value is just the positive value. So it's e to the minus 0.7x minus j 2 pi ux dx. And to make this a little bit easier, I could reverse the limits of this by letting x primed equal minus x. So I'd have two integrals from 0 to infinity. And if I let x prime equal minus x, this would be e to the minus 0.7x plus j 2 pi ux, or these are my x primes, dx prime. And this integral would stay the same. Okay? So now if we rewrote this value of h of u and 0, the indefinite integral of this is just 1 over the argument evaluated between the limits, so it's simply 1 over minus 0.7, not x, minus 0.7 plus j 2 pi u. This would be evaluated from 0 to infinity. And I have another one from this integral. Minus j 2 pi u, evaluated from 0 to infinity. And if we evaluate these, no, I also have the exponential term. 1 over that times the exponential term the same way. So this is a damped sinusoid term in the numerator. Now I have to evaluate it from at x equal infinity and x equals 0. So the first term, when x is equal to infinity, this sinusoid would be damped by e to the minus x, so it would go to 0. And I would subtract the term at x equals 0. And at x equals 0, the numerator is 1, so I have a minus 1 divided by this quantity. And then this evaluation is exactly the same. So at x equal to infinity, again we have a damped sinusoid, so it would go to 0, and at 0 we would subtract that value. So we get plus a minus 1 over minus 0.7 minus j 2 pi u. Now I have a sum of conjugate terms, and all I would have to do is simplify this a little bit by forming a common denominator as the product of these. It would be this term squared plus this term squared. And the numerator terms would be the negative of this one plus the negative of this one. So it would actually just turn out to be 2 times the 0.7 term, or 1.4. Okay, this is h of u and 0. Now, since it's a circular symmetric function, I could change, this would be only one profile between there, but I could change this into an h of r that would have to be exactly the same. 1.4 divided by 0.49 plus 4 pi squared r squared, where this is a radial frequency, r squared would equal to u squared plus v squared. So this is the two-dimensional Fourier transform corresponding to the line spread function. It was given. To get from here to the point spread function does involve a Hankel transform. So we have this circular symmetric function, and there are a lot of places that give the two-dimensional Hankel transform inverse of this as a fixed solution as well. Okay, so notice that if we review the steps of how we've solved this in an easy way, it's exactly the same discovery that's at the basis of three-dimensional reconstruction. Any questions on getting this solution? Pretty easy. Once we see the trick. Let's go back to this board and review the trick in this particular problem. It just shows the beauty of mathematics. And as far as I know, Ron Bracewell was the first to write a paper in 1955 that used this particular idea, but this same idea was also in Papoulis' Systems and Transforms with Applications to Optics books that was written in 1969, where the basic thing that was observed was that the one-dimensional Fourier transform of the line spread function gave us one slice in the two-dimensional Fourier transform space. The only other concept that's necessary to add to this to do three-dimensional reconstruction is simply us noting that if we rotate a function, we rotate its Fourier transform exactly the same way. Okay, and that is a well-known fact in optics, where you can take an image, put it on the optics bench, compute the Fourier transform at a different location. So if this were the image and this were its Fourier transform, certainly if you rotate the image, you rotate the transform. We could also easily prove it mathematically. It just takes a little bit more time than I would like to spend tonight. But notice what happens if we can do that. Here, we've just computed h of u and 0 from this profile function or line spread function. And we've gotten one line in the two-dimensional transform space. If we now computed another profile function at a rotated angle, computed its one-dimensional transform, we would get another slice of the two-dimensional transform space. If we did it at yet another angle, we could get another slice of the two-dimensional transform space. Notice that if we did this systematically for many different angles, we would arrive at the full h of uv. True, it would take an infinite number of rotational angles to fill this space completely, but it certainly would fill it. Then, all we would have to do is an inverse two-dimensional transform to get h of xy, the two-dimensional image function. So it's one of the neatest, non-obvious techniques that is involved in image processing, and that's why we devote even an entire chapter of the text to this particular problem. It's a billion-dollar industry, building machines that can do this computation just for medicine, and the industrial applications have just started. Let's look at what this means to us in general. The profile function would only have to come this way, and we could reconstruct the entire image as it was looked at this way. So in medicine, the typical applications, the profile functions are computed through the body, going front and back or somewhere through the body. The image that's generated is a picture of a slice of the body in the same way. You can imagine someone eventually setting this problem up to determine what the core of the Earth looks like. Right now, no one really knows what the core of the Earth looks like. But if we could project some type signal through the Earth and collect its projection function on the other side at a series of different angles, then we certainly could reconstruct a cross-section picture of the Earth. No one has done that yet. Maybe it takes a stronger radiation source than we've got available, but it certainly is theoretically possible to see what a cross-section of the Earth looks like. Ron Bracewell's initial application was in radio astronomy, where they wanted to determine what the cross-section of a star looked like when all they would see is this front projection. And the rotations in astronomy occur pretty naturally by the orbits of the planets. So it was a very natural solution to that problem. So let's, yes, sir?
How does the scanner work? Does it constantly evaluate that interval?
Yes. Notice that h of xy here is really an arbitrary function. It could be the function that corresponds to the density, maybe for radiation, the absorption density of tissue at any cross-section. All we do is send a radiation beam through, take the logarithm, and you get an integrated function like this at each particular xy point. So you take the line spread function, take its one-dimensional Fourier transform, and this is the first method of computing this was this straightforward, of getting projections here in the two-dimensional Fourier transform plane until we filled up the entire plane, perhaps by interpolation. That would give us h of uv. We have the Fourier transform program to give us h of xy. But we'll see now that there's a very interesting simplification of this problem so that we never have to do this two-dimensional transform. Ramachandran and Lankashiram, if I get the names correctly, developed a convolution algorithm that avoids this two-dimensional transform step, so that this entire reconstruction procedure can be done by simply one-dimensional transforms or one-dimensional filtering and an integration. So that was the beautiful simplicity. It's interesting in terms of the Nobel Prize winners that the first machine patented for doing this type of operation for human data with an X-ray source didn't propose this particular solution that had been in the literature since '55, and the patent was given in 1971. It proposed an algebraic solution to the problem, and to this day I don't believe anyone can prove that the algebraic solution always works, but it's maybe a simpler way to think about it. But then within a few years after that patent, someone showed them this particular algorithm, and the convolution algorithm, as I understand it, is the one that's now implemented. It's the high-speed algorithm on most computed tomography type machines. The industrial applications of this same process are just now getting machines built to do them. But you can think of non-destructive testing, where you can look inside any metal or anything that you could send a signal through and get a cross-section picture to see if it has holes in it or to see what the internal structure looked like without having all the superimposed data that you would normally get with a regular X-ray system. And someday we might do this and see that the core of the Earth really is molten or not molten. But the important thing, I think, was that this key idea of relating a projection function, and now the formal name for a function like this is a profile or a projection function. It's very different from the normal orthographic projections where we normally think of on a line drawing. When we do an orthographic projection, if we have one or more points that map into the same point, we only give it a magnitude of 1. And where there are no points, we give it a magnitude of 0. Whereas this type projection function integrates these gray levels and will keep track of the sum of them. So our integral is really just a sum of all the values across an array. There's even a machine now on the market that does reconstruction of heads, of bust of heads, down to the detail of my wavy hair, even to mustaches and things, that uses some reconstruction techniques like this as well. And every machine that's been built that have been based upon this principle has been a tremendous breakthrough in the field. The medical application, for example, every major hospital in the country now has one or more machines that do this. It's the biggest moneymaker in image processing ever. Maybe except for TV. If we ever get digital TV, that will rival it in terms of money. Let's look at a few slides now that show us the principle that we're working with in three-dimensional reconstruction, and then we'll try to look at the convolution algorithm in some detail to see the key part for it as well. So I'm going to turn the slide projector on. I believe it's in focus tonight. Okay, this just tries to illustrate that there are many ways where we can reconstruct three-dimensional data from transverse cross-sections. One of them is by a transmission type technique. And this is the mode used in computed tomography in the medical applications, transmitting an X-ray beam through your body and usually detecting over here to very high sensitivity the number of X-ray photons coming through. The X-ray attenuation is exponential. So if we take the logarithm of that exponent, it turns it into a linear sum of attenuation coefficients for each cell multiplied by the transmission through each cell. So we can form a transmission function at each particular point in an output plane, and if we do that for this entire line, we would get a line spread function of this slice of the three-dimensional object. Okay, so one class of machines could be built upon the transmission principle. Another entire class can be constructed on the emission principle, and for example, Ortec Corporation in Oak Ridge built, I believe, the first and still build very many of emission computed tomography devices. These devices are based upon the fact that a positron, when it annihilates, would generate two gamma rays that are 180 degrees in direction apart. So that if counters are put around these positions, we could look at the coincidence of points and tell where they're coming from in terms of this two-dimensional array. So it's a different integration effect, but it essentially gives us the same type phenomena of how many positrons are emitted from each particular cell in this discrete representation of the three-dimensional object. The three-dimensional reflection problem is, I believe, the principle of the one built for doing bust of human heads and of fixed objects. And they could either be built to get surface characteristic reflections with light, electrons as an electron microscope imaging. So these techniques also apply to trying to do three-dimensional reconstruction of DNA molecules and other things like that. Radar would work, and even ultrasound would work, where there are special properties of the absorption at different depths due to ultrasound. But there are many modes where we can use a sensor of some type to give us profile functions of a three-dimensional object. If we can reconstruct just one cross-sectional image, we could then argue that we can construct the entire three-dimensional image, because we'll just stack these into a three-dimensional matrix. And in fact, we could then look at the image not only from the top down, but from this side, or at a diagonal, or in many different ways. It would be a very unique image. For example, the apple that we looked at was just put together in a slightly different way, but we actually sliced this one and stacked the slices to make a three-dimensional type object. In the medical tomography, this is more of a schematic of how a medical CT machine would work, and if we could adjust the brightness, this might show up a little bit, or have it a little bit too bright.